Let's look at one of the distributive laws. A intersecting B union with C is equal to A intersecting B union with A intersecting C. So we can take the A and distribute it in through these brackets here. A intersecting B union with A intersecting C. The other distributive law is got by replacing this intersection with a union and this union here with an intersection and doing the same over on the right hand side. Now, we proved this law in the previous video by drawing diagrams. In this video, I will show you a general method for proving set properties that does not involve drawing diagrams. The general idea is the following. Suppose we have to prove that some set D is equal to some set E. So D could be made up of many intersections and unions of different sets. Similarly for E, we have to prove this. What we do is we start by showing that D is a subset or equal to set E. That means that D is contained in E or could equal E. The second thing we do is prove that E is a subset or equal to D. That means that E is contained in the set D. Now, if both of these things are true, then we can only deduce one consequence, and that is that D must equal E. Because if D is contained in E and E is contained in D, then D and E must be the same set. So this is the general method that we will use. You might wonder, how do we prove that a set is a subset of another set? Well, what we do is we pick any element in this set, we call it X. Let's say X is an element of D. So this symbol here means that X belongs to set D. And we try to prove that X is also an element of E. So if X is any element in D, X stands for any element of D, we need to prove that that element is also in set E. That's how we can prove that D is a subset of E. So let's go back to our problem. We're going to try and prove that this side here is a subset or equal to the right hand side. So this is step one in our proof. So we take any element X in this set, and we need to show that that element is also in the set on the right hand side. So let X be an element in A intersecting B union with C. Let's look at the consequences of this. If X is in the intersection of A and B union with C, it means that X is in both sets. X is in set A and X is in B union with C. Let's look at the fact that X is in B union with C. If X is in B union with C, it means that X is in B or X is in set C. So it could be in one of these sets, but it must be in at least, well, not at least, but can only be in, well, it could be in both of them. It could be in the intersection of them, of course. So B union with C looks like this. So X is some element that's in the union. It could be anywhere. It could be here, or it could be here. So it's either in set B or it's in set C, or it could be in both. Let's suppose that X is in set B. What can we deduce from that? Well, we already know that it's in set A. So if it's in set B as well as set A, then it must be in both A and B. It must be in the intersection of A and B. But if X is in the intersection of A and B, then it must be in the right hand side, because the right hand side consists of A intersecting B union with A intersecting C. So if X is in here, then it's in the union of A intersecting B and A intersecting C. So I'll just say right hand side here. I don't want to write down all of that. Now the other possibility is that X is an element of C. But since we know that X must be in A, then if it's both in A and in C, it means that X is in set A and set C, the intersection of A and C. That means it's in here. But if it's in the intersection of A and C, then it must be in the union of A intersecting C and A intersecting B. Because the union just adds something onto this. It doesn't take anything away. So that this here implies that X is an element of the right hand side. So it doesn't matter. So whether X is in B or in C, we still conclude that X is in the right hand side. So if we start off by saying that X is any element in this set, we've ended up showing that X must be in this set here. That tells us that this set here is a subset or equal to this set here on the right hand side. So that's step one in the general method. Now step two means reversing this. So we want to show that this set here is a subset or equal to this set over here. So to prove this here, that the right hand side is a subset or equal to the left hand side of the property that we're trying to prove, we take any element X that's in this set here and we try to show that that element is in the set on the right hand side over here. So X is any element in this set. So let's deduce the consequences of X being in this set here. If X is in the union of two sets, it's in the union of this set with this set, it means that X must be in one of these sets, because the union is got by putting these two sets together. So X must be in one of them, or it could be in both of them. Okay, so let's take this further. Let's suppose that X is in A intersecting B, and then we'll take the other case afterwards. If X is in A intersecting B, it means that X must be in A and it must be in B. So you can think of the intersection as the AND operator, like in logic. Now, let's just have a quick look at the right hand side here. If X is in A intersecting B, then X must be in the set B. But if X is in B, it means that X must be in this set here, B union with C. Because to get B union with C, we just add C onto B, that's all. So if X is in B, it's obviously in B united with any other set. But now we've proven that X is in the right hand side, because we've shown that X is in set A, and which is this set here, and we've shown that X is in set B union with C. So X is in both of these sets, which means it must be in the intersection. So that tells us that X must be in the intersection of these two sets, A intersecting B union with C. So that's the consequences of X being in A intersecting B. But remember, we have a choice here. It's either in A intersecting B or A intersecting C. So now let's look at what will happen if X is in A intersecting C. Well, that just means it's in both A and C. And similarly, now we can show that if X is in C, well, it's obviously in the C united with any other set. It's in B union with C. So X is in A and it's in B union with C. So it's in both of these sets here. So that tells us that X is an element of the intersection of them. So either way, we end up showing that X is an element of the right hand side. So if X is any element that's in this set here, then it's automatically in the right hand side. So that tells us that this statement is true. So we showed earlier that 1 is true. Now we've shown that 2 is true. And the only consequence is that our original statement must be true, that both sides must equal each other. Now let's look at one of De Morgan's laws. So the step one, as we saw before, is to prove that the left hand side is a subset or equal to the right hand side. So to prove that, we let X be any element in the set on the left hand side, that is A union with B complement, and we need to show that this element X is also in the set on the right hand side, A complement intersecting B complement. Well, this only means that X is not an element of A union with B. If it's in the complement of A union with B, then it cannot be in A union with B, because A union with B complement and A union with B are disjoint sets. They have no elements in common. So either X is in the set or it's not in the set. But if X is not in A union with B, it means that X cannot be in set A, because A union with B includes set A, and it cannot be in set B, because A union with B includes set B. But if X is not in set A, it means that X must be in the complement of A. And if X is not in set B, it means that X must be an element of the complement of B. The complement of B is everything outside of B. But if X is in both of these sets, A complement and B complement, it means that X must be in the intersection of the two sets. If it's in both sets, it's in the intersection. So we've shown that if X is an element of A union of B complement, then it must be an element of A complement intersecting B complement. So we've proven this case. The second step is to prove that the right-hand side, A complement intersecting B complement, is a subset or equal to the left-hand side, which is A union with B complement. So again, we let X be any element in A complement intersecting B complement. We let X be any element in the set on the left-hand side, and we need to prove that that element must be in the set on the right-hand side. So what are the consequences of X being in A complement intersecting B complement? Well, if X is in the intersection of two sets, it must be in both of the sets. Now, if X is an element of A complement, it must mean that X is not in the set A. So X must not be an element of A. Any element is either in a set or it's not in the set. So if it's in A, then it can't be in A complement. A complement is just everything outside of A. And vice versa. If it's in A complement, that's everything outside of A, then it cannot be inside set A itself. Similarly here, if X is an element outside of set B, then it must not be an element of B. It must not be inside set B. So X is not an element of A and X is not an element of B. That means if we unite A and B together, X cannot be an element of A union with B, because A union with B is just A and B put together, of course. But if X is not an element of A union with B, if it's not in this set A union with B, then it must be outside of it. That means it must be in the complement of A union with B. And now we're done. We've proven that if X is an element of this set here on the left hand side, then it must be an element of the set on the right hand side, which shows that A complement intersecting B complement is indeed a subset or equal to A union with B complement. So we've proven that this is true. So just like in the previous example, from 1 and 2, we conclude that A union with B complement must indeed equal A complement intersecting B complement. In this next section, we're going to look at how to prove set properties using the rules of sets, which are given in this table here that I covered in the previous video. So the first example, we want to prove that A union with A complement intersecting B equals A union with B. Well, we can start by using the distributive property. We can distribute this union in through this bracket here to get A union with A complement intersecting A union with B complement. Sorry, A union with B. Now, A union with A complement is just a universal set. That's the complement law here. A union with A complement is U. And we want the intersection of the universal set with A union with B. Well, we could turn it around by using the commutative property, which is that A union with B is the same as, or sorry, A intersecting B is the same as B intersecting A. We could turn this around, but we don't really have to. We use the identity law to show that if we intersect any set with the universal set, we just get that set. And that makes sense. I explained that in the previous video. So we end up showing A union of B intersecting U is equal to A union of B. So we've proven this property. In the second example, we want to prove that A intersecting with B complement intersecting A complement is equal to A intersecting B complement complement union with A complement. Let's look at the left hand side here. We want to consider the complement of B complement intersecting A. Now it says here double negation, but actually we have to use one of De Morgan's laws first to break down this thing inside the brackets. So we have the intersection of two sets, the complement of the intersection of two sets, that's covered as one of De Morgan's laws. So we take the complement of the first set united with the complement of the second set. So what we have to do here is to take the complement of the first set inside the bracket, which is B complement. So we have to get B complement complement and unite that with the second set, which is A. And we have to take the complement of it. So I'm just following De Morgan's laws. We take the complement of each of these two sets and unite them. But now we then use double negation. B complement complement is just B. And we have to unite that with A complement. Now we can use the distributive property to distribute the intersection in through the brackets here. So we're using the second distributive law here. So this becomes A intersecting B union with A intersecting A complement. Now the intersection of A and A complement is empty because A and A complement are disjoint sets. They have no elements in common. Either an element is in A or it's not in A. It can't be in both sets. If we unite any set with the empty set, we just get that set because there are no elements in the empty set. So that's known as the identity law. That's this law here. A union with phi is just A. So just as a correction, we should have De Morgan in here. We used one of De Morgan's laws first before using the double negation. Actually, there is another misprint here. We're trying to prove that this statement here is equal to A intersecting B. Okay, that's missing on top. That's what we were trying to prove actually. This line here just comes from applying De Morgan's law to this thing here, which I talked about earlier. To get the complement of the intersection of two sets, we get the union of the complements of these two sets. So we get B complement complement union with A complement. Now let's look at example 3. What we can do to the left hand side here is start by applying De Morgan's law to this set of brackets here. We have the complement of the union of two sets. So the complement of A union of B is the intersection of the complements of the two sets. So we start by getting the intersection of the complements of A complement and C. Now A complement complement is just A. That's where this A comes from. And then we have C complement and we get the intersection. So we're using double negation as well, of course, because we had A complement complement giving A. Now let's take a look at this statement here and apply the distributive law. We just pretend that A intersecting B is just one set and we want to unite it with the intersection of these two sets. So the distributive law we're using is this first one here. We want to unite a set with the intersection of two sets. So we unite that set with each of the two sets and take the intersections. So we want to unite A intersecting B with A. That's what we have here. And we want to unite A intersecting B with C complement. And we want to take the intersection. Okay, so that's just the distributive law. It's this distributive law here where we're intersecting the two sets. Because we have an intersection in here. So that's all. We just pretend this is one set. And then we can apply the distributive laws again to this set in square brackets and to this set over here. So I'll write what we get over here. So we want to take A intersecting B and unite it with A. Well, we can just unite A with A and take the intersection of that with B united with A. Okay, you're not used to seeing the distributive law written like this. It's the distributive law turned around actually. But of course we can turn it around by the commutative law. It doesn't matter which way we order these. So this is just the distributive law where the set that's made up of two sets is shown first rather than shown second. But we can still do the distribution, of course. And we want to take this set and intersect it with this set over here. So this is A union with C complement intersected with B union with C complement. Now, let's look at this first bracket here. A union with A is just A, and we want the intersection of A with B union with A. Now, this is actually one of the laws. It's called the absorption law. A intersecting A union with B is just A. So we can replace all this square bracket with A. The absorption law is not mentioned here, but that's what I'm using here. And we want to take A and intersect it with this set over here. Intersected with A union with C complement. Since we're getting the intersection, it doesn't matter which two we take first. That's from the associative laws. We're taking the intersection of three sets. Doesn't matter which two we take first. We can effectively drop the brackets here. So we have three sets here. This one is A. We have this set as our second set, and this is the third set, and we're intersecting the three sets. So I can just drop brackets. So this is A here, intersecting with this set and intersecting with this set over here. Doesn't matter which two we take, but if we take A intersecting this set here, the answer is actually A, because what elements do we have in common here? Well, if an element is in A, then it must be in A union with some set. And if an element is in the union, if it's in this set here, we also want it to be in A. So the union of A with A, sorry, the intersection of A with A union with something is A. Actually, that's one of the absorption laws again. A intersecting A union with B is just A. That's the situation we have here. We replace B in the absorption law with C complement. So the left hand side boils down to A intersecting B union with C complement, and there's not much we can do with that. The method that's given here is to stop at this point with the left hand side and then just consider the right hand side and simplify the right hand side until hopefully we end up getting this expression here. Let's look at just this bit first and apply the distributive property. So treat A union with B as a single set, and we want to intersect it with the union of these two sets. So we're using this distributive law here, A intersecting B union with C. So we intersect A with B and then we intersect A with C and we unite the two sets. So here we take this set A union with B and intersect it with the first set. So I'll put brackets around it here. And then we unite it with this first set A union with B. Intersecting the second set, which is B complement. Now we can use the absorption law here on this first set. A union with B intersecting A is just A, whereas the absorption law turned around. So this set here is just A. So I'll write it over here. And we want A union with this set here. A union with B intersecting B complement. So a lot of the detail is missing here. We apply the distributive law in here, and we take the intersection of B complement with A, which is what we have here, union with the intersection of B complement with B, which is what we have here. Now, the intersection of B with B complement is the empty set, because B and B complement are disjoint. They have no elements in common. So this is just phi. So we have A intersecting B complement union with the empty set. Well, if we unite any set with the empty set, we just get that set. That's one of the identity laws. A union with phi is just A. Now we can apply the second absorption law. A union with A intersecting B is just A. So A union with A intersecting B complement. It doesn't matter what this set is just A. So that's what's arrived at here without much explanation. So we end up getting A for all of this here. and we want to take A and intersect it with this set here. The distributive law is used here on this. We just group B union C complement as one set. So we want A intersecting A complement union with A intersecting B union with C complement. A intersecting with A complement is the empty set. As we've seen before, that's one of the laws. That's the complement law. So we end up uniting the empty set with A intersecting B union with C complement. But of course, if we unite the empty set with any set, we just get that set. That's one of the identity laws. It's covered up here. A united with the empty set is just A. So we end up getting the same thing on both sides. So in this example, it was easier to take both sides and break them down until we got the same thing, which proves this example.